In this video, we'll see lots of animations of wheels going back and forth, sometimes rolling up a curve and sometimes unrolling a curve. In this example, we'll come to the details later, but what is going on is that we are rolling up this sawtooth and unrolling an approximation to it in terms of sinusoids. The general name for this kind of thing is Fourier-analysis, after this guy. Here, in approximating a sawtooth with sinusoids, we're actually trying to approximate a discontinuous function using very smooth functions. So it's not surprising that we're struggling to get a tolerable approximation. Still, if you add enough sinusoids, you can get an arbitrarily good approximation. And in fact, any curve you can draw can be approximated in this way. There are better animations online. Here's one with gears on gears, tracing a complicated function. It is an animation, not a real machine, though it fooled me at first. This one is definitely not an animation. It's a Fourier-analysis machine from the 19th century, designed by Michelson. Yes, that Michelson, the one who made interferometers. And then there's the Antikythera mechanism, a nondescript mass of corroded bronze found in a shipwreck from ancient Greece.
What you're seeing here is X-ray slices through the main surviving fragment of the Antikythera mechanism. You can see all the details of the gears, the pins, the bearings, the arbors, the inscriptions. It's a truly complicated device.
The gearing mechanism transforms an input rotation into all sorts of complicated rotations, including tracing the motions of the moon and planets across the sky. I guess this must be Mercury. How do you choose all the right gear wheels to make it dance back and forth like that? We would use Fourier-analysis, but ancient Greek engineers would have used geometrical ideas. Can we understand Fourier-analysis in completely geometrical terms? Let's try. With some inspiration from two superb videos, this one by Mathologer and this one by 3 Blue 1 Brown. For starters, let's just draw a cosine curve. Here we have a rolling wheel, and on that wheel we have this offset blue circle which goes through the axle of the wheel. The blue dot is like a paintbrush which can move around the blue circle but has to be vertically aligned with the axle of the wheel. This paintbrush traces out a cosine curve. Here we see 3 cycles. If we want a sine curve instead of a cosine curve, we just change the phase by changing the initial orientation of the blue circle. The yellow dot at the center of the blue circle actually specifies the blue circle, because the blue circle is constructed to pass through the axle of the main wheel. So all the information in the blue circle is encoded in the yellow dot. That information is the amplitude and the phase. The other piece of information specifying the curve is the wavelength, and it's given by the radius of the main wheel. The wavelength is just 2 pi times the radius. So with this smaller wheel, we have a shorter wavelength and 3 cycles in the same horizontal range. Little n is our horizontal coordinate, and it goes from 0 to 255. Big N is 256. We can run the wheel backwards and roll up the curve instead of drawing it. But what if we roll up the curve using a wheel of a different size? We don't get back our blue circle. Instead, we get a nice pattern centered around the axle of the wheel. If we now think of the yellow dot as the centroid of the rolled up pattern, the yellow dot is on the axle. That is to say, if we mismatch the wheel to the wavelength, the yellow dot will give us 0 amplitude. Next, let's try something a little more complicated. Let's take this 2-cycle curve and this 3-cycle curve and add them, and then roll up the result in a 2-cycle wheel. We get a curious looking asymmetric pattern. The centroid of the pattern is marked as before by the yellow dot, and the position of the yellow dot is the same as we had when we unrolled the 2-cycle curve. Let's roll up the same curve again, this time with a smaller wheel that does 3 revolutions. Again, we get an asymmetric pattern, and its centroid corresponds to the original 3-cycle component. Thus, rolling up a curve in different sized wheels tells you the amplitude and phase in the component with the matching wavelength. That's Fourier-analysis stated without equations. If we do want equations, here's the expression for the recovered yellow dot. Here r is the radius of the wheel. Here it corresponds to 2 cycles. The rolling up operation takes the curve or signal value s sub n and rotates it by n over r radians. In the complex plane, rotation by n over r is multiplication by exponential of n over r times I. By the way, in these animations, the real axis is vertical and the imaginary axis is horizontal. If we wanted the standard orientation of the complex plane, we'd have to rotate the whole animation, which doesn't look so nice. With the angle brackets, we consider the average value of the rolled up signal, which is to say the location of the yellow dot at the end. We can call this amplitude A sub r, corresponding to wheel radius r. Instead of the wheel radius r, we may prefer to think of the number of cycles. The number of cycles, let's call it k, is the total length, big N, divided by 2 pi r. Rearranging, we get exponential of 2 pi I over big N times kn. Here k equals 2 for 2 cycles, and we recover the corresponding amplitude A sub k. Here we have k equals 3 for 3 cycles, and here we have k equals 4, which wasn't in the original signal, so the recovered amplitude is 0. The inverse expression for the curve or signal s sub n for given A sub k looks a bit more complicated, but it isn't really. We are taking the amplitude A sub k and rotating it in the opposite direction. So the argument of the exponent is minus 2 pi I over big N times kn. Then we add the complex conjugate of the whole thing to get twice the real part. Why 2 times the real part? That's because A sub k, or the yellow dot, represents the radius of the blue circle, whereas the amplitude is given by the diameter of the blue circle. And to conclude, let's revisit the sawtooth. Roll it up with k equals 1, unroll the k equals 1 component, roll it up with k equals 2, unroll the k equals 2 component, show the sum of the components so far, continue with k equals 3, and so on.